Alright, this is the fifth and final video for chapter 14. We're talking about solutions. And one thing we're going to talk about now is colligative properties of solutions. If you have a pure solvent or a pure compound, it will have a set of properties, individual properties for that solvent or compound, such as melting point, boiling point, index of refraction, density. When the solvent or the pure compound becomes a solution, it's no longer a pure compound but a mixture. The term colligative property refers to solutions, and these are any properties of a solution that depend on the number of the number of solute particles dissolved in the solution, and not the nature of the particles themselves. Which means, if you have a solution, and that solution has a certain volume or kilograms of solvent, and if in that, let's say 100 kilograms of solvent, let's say that there are 1, 2, 3, 4, 5, 6, 7 particles dissolved. If those particles, let's make it 8. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. 4. If those particles are sodium cations and chloride anions, we're not worried so much in a colligative property about what the identity of those particles are, just the number of particles. This has 8 particles dissolved in this certain mass of solvent. If instead of sodium and chloride, if we have 8 particles dissolved and those particles are, let's say, magnesium and hydroxide. Instead, it doesn't matter what the identity of the particles are. Colligative properties are these physical properties of the solutions that only depend on the number of particles present. So there's 2 colligative properties we're going to look at, and those are melting points and boiling points of solution. I could have, let's say, 8 particles of sodium chloride dissolved in water. Or I could have 8 particles of magnesium and hydroxide dissolved in water. And because they contain the same number of particles per kilogram of solvent dissolved in them, or the same concentration of particles, we should say, not the identity of particles, these 2 different solutions will actually have the same melting point and boiling point. That's what it means to be a colligative property. Let's see here. So what happens when we dissolve particles into a solvent? Especially if that solvent is something like water, that's usually what we look at. But what happens when we dissolve particles into any solvent? You can read about why this is in your book. I just want to really explain what happens. What happens is the vapor pressure of the solution is lower than the vapor pressure of the solvent itself. All right? Dissolving a solute into a solvent lowers the vapor pressure of the solvent. Now remember what vapor pressure is. Let's say we have a pure solvent here. And here we have a solution with ions dissolved in that solvent. Remember, the vapor pressure is the pressure of the vapors that escape in a closed container, pushing back against the surface in an equilibrium process. When we say that in a solution, the vapor pressure is lowered, you have a lower vapor pressure in a solution than the pure solvent, that means the particles of the solvent escape less in the solution, because there's a lower pressure pushing back on them, than they do in the pure solvent. Why might that be? Well, remember that like dissolves like. So polar solvents dissolve ionic compounds generally. So the partial charges of the polar solvent likes the full charges of the ionic compound, or the partial charges of a polar covalent compound, And the particles of the solvent interact with the solutes, and they have strong interactions. Those stronger interactions hold the particles of the solvent into the solution more, and there's less of them escaping. So if there's less escaping, there's a lower vapor pressure. So that's the short answer of why the vapor pressure is lowered. Now, what does that have to do with the colligative properties? If you lower the vapor pressure of the solvent, in order to reach atmospheric pressure by increasing the temperature to boil, remember the vapor pressure has to equal the atmospheric pressure in order to get a boiling point. If you have a lower vapor pressure, so let's say here's your pure solvent, you have a certain vapor pressure, pure. And here, let's say this is atmospheric pressure. Atmospheric pressure doesn't change. And when vapor pressure equals atmospheric pressure, by increasing the temperature, you have boiling, okay? But if you have a solution, your vapor pressure of your solution is lowered, it requires much more temperature, or an increase in temperature, in order to boil the solution. So what we end up with is increased boiling points. They boil at actually higher temperatures. Also, the freezing point decreases. So you get boiling point elevations, or an increase in boiling point of the solvents. When you dissolve something in a solvent, your boiling point increases. When you dissolve something in a solvent, your freezing point decreases. Now, you've probably seen these examples before in everyday life. For instance, the radiator in your car. You could put water in the radiator of your car, and it would operate fine under mild temperatures. However, in the heat of the summer, with the heat of the engine and all of that going, water boils at 100 degrees Celsius. So in order to keep your engine cool, what you do is you have the water flowing in there, right, to keep the engine parts cool. You don't want the water boiling, though. So what's done is they take ethylene glycol and they mix it with water, and they create this substance called antifreeze. Antifreeze does two things. It boils at a higher temperature, so the boiling point's much higher. You don't have all that pressure inside your radiator versus the regular water, even though there is some. But also, think about the dead of the winter. If you had water sitting in your radiator in Wisconsin in the middle of the winter, that water would freeze at 0 degrees Celsius, 32 degrees Fahrenheit. If you dissolve the antifreeze, ethylene glycol, in copious amounts of it inside the water, get a nice viscous solution, because with more particles dissolved, you lower the freezing point, and you end up keeping the liquid at lower temperatures. So it keeps you from boiling too high and getting too hot. It keeps it from getting too cold. So it basically increases the temperature range. So here's the normal boiling point of a solvent and the normal freezing point of a solvent. The boiling point becomes elevated. The freezing point becomes depressed, we would say, or lowered. And you end up increasing the window in which your solvent is a liquid. Higher boiling points, lower freezing points. So the colligative properties are properties based on the amount of particles, the number of particles dissolved in that solvent. So if you have more particles dissolved in the solvent, your boiling point will get higher and higher. If your freezing point will get lower and lower. You can actually calculate the change in the boiling point and freezing point using chemical properties, using these equations given. So if you want to calculate the change in the temperature for the boiling point, okay, now this is not the new boiling point, this is the change in temperature. You're going to say the molality times a constant for that solvent called the boiling point constant, Kb. So the change in temperature and boiling point of any solvent, change in temperature boiling, is going to equal the molality of the solution times the boiling point constant, which is found on a chart, or it's usually given for each solvent. Now, what is molality? We talked about molality earlier. We said it was the number of moles of solute per kilogram of solvent. Okay, the moles of solute particles per kilogram of solvent. We can calculate the freezing point depression the same way. The freezing point change will equal the change in temperature freezing is the molality times the freezing point constant, K. And that can be found, that constant, on a chart, or it can be given to you usually as well. You probably don't have to memorize, you won't have to memorize those will be given to you. So these two equations shown right here, which I'm going to erase that now, because I'm done talking about it, can be used to calculate the change in temperature of boiling or freezing. What if I ask you, what's the new temperature, the new boiling point, or the new freezing point now that I've dissolved these particles in the solvent? Well, if this is the change in temperature, you've got to either add or subtract from the initial boiling point. For instance, the initial boiling point of water is 100 degrees Celsius. If I throw salt in there, I calculate the change in boiling point. Boiling points are elevated, they increase. So you add the change to the initial boiling point of the solvent. Because freezing points depress or become lower or decrease, you subtract the change from the freezing point of water. For instance, the freezing point of water is 0 degrees Celsius, so you subtract the change, and that will give you your new freezing point of the solution. Are your solutions always water-based? The answer is no. In your book, or given on an exam or something, you'll always be given the physical constants you may need to solve a problem. Now, what would you need to solve a colligative properties, boiling point, freezing point problem? You're usually either going to need the freezing point, if you're asked to calculate the new freezing point, the initial freezing point of the solvent, or the initial boiling point of the solvent when it was pure. And you're also going to be given either the freezing point constant or the boiling point constant. And you can calculate the molality that will usually be given to you in the problem. So let's go ahead and let's work some problems based on colligative properties. Alright, this first problem here says, what is the freezing point of an aqueous solution? So what is our solvent here? Aqueous means water, right? So we're going to be looking at the properties of water. So we might need some of these constants, these physical constants given here for water. It says, what is the freezing point of an aqueous solution prepared by dissolving 0.1 moles of sugar into 0.5 kilograms of water? The normal freezing point of water is 0 degrees Celsius. The normal freezing point constant for water is 1.86 degrees Celsius per molal. That's short for molality. Okay. So we're actually given those constants in the problem. So I just want you to see, in your book, if you're given a problem, or maybe online, you're not always given the constants, but you can find them in your tables in your book. On the exam, however, I'll probably give you the constants somewhere so you can look those up. All right. It says here, what is the freezing point? So if we want to know the freezing point of a solution, it's different from the freezing point of the solvent itself. So remember that the freezing point, the new freezing point, is going to equal the initial freezing point. And remember, our freezing points increased or decreased? Freezings are decreased even further. It'll be the initial freezing point minus the change in temperature of the freezing point due to the solubility of the particles in the solution, the lowering the vapor pressure. So we're going to subtract the change. Alright, now, we don't know the new freezing point. That's actually what we're asked to find. But what we do know is the initial freezing point of water. It is 0.0 degrees Celsius. 0.0 degrees Celsius minus TF. Change in TF, delta TF. That's our change in freezing point. We're not given that. We're given moles of sugar in kilograms of our water. We're going to have to calculate the change in temperature through molality and the freezing point constant. So I'm going to come over here. The change in the freezing point, these equations will be given to you, but you'll have to know how to use them and in what order. The change in freezing point is always molality times the freezing point constant. So molality, we said, was moles of our solute, here's the sugar, 0.10 moles of the sugar, divided by kilograms of solution, or solvent, kilograms of solvent. So here we have 0.50 kilograms of our solvent. So that's our molality. 0.1 divided by 0.5, what is that? 0.2? 1/5? All right. Times Kf, our freezing point constant, which is 1.86 degrees Celsius per molal. All right. Let's go ahead. The change in temperature of freezing, let's recalculate that, equals 0.1 times 0.5 gives us 0.2 molal times 1.86 degrees Celsius per molal. So the molals cancel out, so the change in our freezing points when we dissolve that many moles of sugar into the water is what? 0.37 degrees Celsius. Notice I got my degrees Celsius left. So that's the change. That's what we're going to put over here. So I've got 0 degrees Celsius minus 0.37 degrees Celsius. So you might be tempted to write negative 0.37 degrees Celsius. But remember, we're to the 10th place here, the 100th place in here. You're only as precise as your least precise measurement, right? So I'm going to round this to the 10th place. So my freezing point will be negative 0.4 degrees Celsius when I put this together. So that solution will be 0.4 of a degree Celsius lower in freezing point than normal water. All right? Let's see if we can do another one. This next problem, number 2, says, what is the boiling point? So now we want to know the new boiling point, right? So let's write that. What is this boiling point? Of a 4.0 molal aqueous solution, so here we're given the molality. It's aqueous, so what's our solvent? Water. Of a non-volatile electrolyte. The boiling point elevation constant for water is 0.512 degrees Celsius per molal. Alright, so we wanted the boiling point of the solution. So if we wanted the boiling point of the solution, we want to actually know the new boiling point, which is the initial boiling point. And remember, boiling points are elevated, plus the change in boiling point temperature of the solution. So we're going to calculate the new boiling point. What is the initial boiling point of water? The boiling point of pure water is 100 degrees Celsius. I bet you already knew that. I'm just going slow here. Alright, so the boiling point of water is 100 degrees Celsius plus the change in temperature of boiling. We need to solve for that first. So the change in boiling point temperature, not the new temperature, but the change, is going to be the molality times the boiling point constant. The molality is actually given to us this time. It's 0.512 degrees Celsius per molal. And the boiling, that's the boiling point constant. What's the molality? The molality is 4 molal. Sorry. So we end up, what's 0.512 times 4? Basically, I'll just write that so you know what I'm doing here. I'm running out of room. It's hard to write with a stylus. 0.512 times 4.00. Okay, and the molals cancel out. We end up getting degrees Celsius. So what is that? So let's see here. I get 2.048 degrees Celsius. So it looks like 3 significant figures. So 2.05 degrees Celsius. Now, stop here because a lot of times students will give me 2.05 degrees Celsius as their answer. But that is not the answer. That's the change in boiling point. Now, if I ask what the change is, give me that answer. But if I ask you what the boiling point is, the specific boiling point, you've got to add that. So we're going to add 2.05 degrees Celsius to the original 100 because boiling points are elevated. So we're going to end up getting, with significant figures, it looks like 102.05, that'll round up to the 10th, 102.1 degrees Celsius.